I'll
recording.
just share.
Yeah,
There we
great,
go.
thank you.
No rush. I'll just make sure this is working as well. If you guys can just tell me when you've got my screen, that would be great as well.
Looks good.
Yep, 1 second. Let me just.
You're not full screen.
Okay, excellent. Wait up. Let me just get rid of my face. Okay, perfect. So I'll proceed, Mike. And look, just to preface this, I think Marianne mentioned it earlier, but we're going to record this so that we can use this presentation for a public consultation and provide this to the public. So I guess all of us know each other fairly well, but if we could just present who we are a little bit more formally today so that we don't have to redo things, that'd also be appreciated. So I'm Leonard, VP of Methodologies here at Puro, and I'll be taking everybody through the methodology draft that has recently been written with quite a lot of painstaking effort. So thank you for all of you for your contributions and help along the way. So I'll do my best to not breeze through things today, but I don't think we need to labor things too much. The document has been shared and will be shared. So the purpose of this is to really give you a walking tour of the document, I guess, so that everybody's clear on why it's been written the way it's been written, why it's been structured the way it's been structured, and the dimensions that are more clear and more unclear, so that we can have a nice dialogue around that today. So I'm more than happy to address questions, but I think for the run of play today, and particularly for making this available to those that can view this as a video that encompasses all, let's just, if we can, hold questions until the end and run through each of the presenters and myself first, and then we can stop the recording and have a dialogue amongst ourselves as we ordinarily do. So let's move on with things. So as has already been introduced, we have Dr. Thomas Rinder joining us today. Thank you very much. Noah, thank you very much. And David, they'll both be addressing topics that I'll introduce right now, but there's some interesting mugshots of them that I was able to find. Hopefully they're appropriate. Okay, so firstly, I'm going to take everyone through an overview of the actual methodology document. So last time there was an overview of the method broadly, introducing a simulation approach from Mel, but today I'm going to take you through the document, which hopefully everybody then has a chance to read and comment on. Thomas will be taking us through a case study of the contamination and toxicity thresholds, specifically in Germany. Excuse me. Noah will then take us through a simulation approach, which is included in the calculation and quantification section of the methodology document. The purpose of this is to, I guess, give everybody a nice practical behind the scenes look at who Noah is, what they're looking at doing, and have him explain that approach to simulation, which I think is really important. And then David will talk, in essence, about the future direction of bringing these simulation approaches and data collection approaches into one house or under one roof, which will be really important for things moving forward. But I won't speak for him. I'll let him continue there. We'll then have a Q&A, so we can stop the recording, have a Q&A, and then have a path forward to finish from Marianne. Okay, so a quick overview of this presentation, what I'll be presenting for you guys. So just as a recap, I guess, where we've been so far on the journey, who's presented, what we're actually talking about today. I know we're all doing various things in our daily lives, so just bringing it all back to a point so that things are clear, and then we can get the best questions and feedback as we roll through. And then I'm going to take everyone, as I said, on a walking tour through the document. I'll try and be concise and snappy and get that done as quickly as possible, but also leave you with the key points for consideration that will then also inform the Q&A for the panel. Okay, so quickly, our previous meeting, as everyone remembers, we don't have Mel here today, but I gave a simplified overview. Ellie gave an overview of her field work and preliminary results, and difficulties with some of that work. And then Mel gave an overview of the 1D reactive transport model that Undo are looking to apply and have done as associated with their 10,000 tonne trials in Scotland. And Paul Knox was here with us last time and again today. Thanks, Paul, for providing a wealth of experience on being involved in the topic for, as he mentioned, well over a decade. Okay, so what are we looking at? Very simply, spreading crushed rock over an area of soil. That's it. And the rock types being considered, such as basalt, silicate rich and contain calcium and magnesium, amongst other elements. Don't think I need to labour this too much, but enhanced rock weathering, it's a natural process. We're looking to enhance or accelerate that process. Normally happens incredibly slowly. We're trying to speed that up, but it's still slow. It's not an industrial process. It's still in soil, in a natural environment. And the result of the process includes carbon stored as carbonate minerals in soil, or dissolved bicarbonates and carbonates that drain into surface waters and the ocean, where they contribute to ocean alkalinity. And maybe some of the other folks today wish to discuss that, and that may be part of our questions. So I think an important one to pause on before we get into the document is, why do we want to start this now? Like, why is this something that's important? So I think it's something that's been considered for probably more than 30 years as an approach to removing atmospheric carbon. It's a natural process anyhow, but not done like this. It's not included in any existing carbon crediting programs. So actually we'll put this approach under the control of standards, which may not otherwise happen. Addressing the scientific uncertainties through field trials and evaluating these practical issues will enable us to really learn a lot more that we need to learn so that this can be done better in the future. And it has a really significant removal potential. I mean, it can potentially be really huge, but there's still a lot that we don't know, and we really need to fill those knowledge gaps. So if we don't start moving in that direction safely, then nothing's going to get done, which I think would also be a shame. Okay, so the document itself, I've shared this with all of you. So I think hopefully everyone gets a chance to read through it in its entirety, whether that's in minute detail or glancing through. But I think useful to point out each of the individual chapters and what I'd like you to focus on, certainly when you are reading through that. So just a brief walkthrough before we get into it. We have an introduction. We have our general principles, which Myers outlined just before the meeting, which may remain in the actual document or be taken out and applied more generally, but certainly still apply to each of our methodologies, but they've also been updated and aligned with ICVCM. We have environmental and social safeguards as a separate chapter in this instance, which I viewed as being important given some of the concerns that are around in this domain, and we can unpack them shortly in a moment, but I think it warranted a separate chapter than just a paragraph within a section. Eligibility requirements and verification, they've all been put in one house now so that we don't have one chapter linking to a chapter at the end. We have what's required and what needs to be verified right beside each other. So I guess just making the document more practical if it's going to be operationalized. Point of creation, I'll take you through that today and the two approaches that we've conceptualized for that. Ilias will take us through the life cycle assessment, and then I'll give a primer and an overview for quantification, which will then be expanded upon as a second approach by Noah today, as I've mentioned. Okay, so let's crack on and just try and get through this. Okay, positive aspects. First, the mineral resources are abundant. Second, they're well-established technologies that we're talking about. So rock mining, grinding and spreading, it's nothing particularly new, but there are trade-offs. and it's expensive in some instances. So third, among the most permanent, this approach is one of the most permanent forms of carbon removal with little risks of reversibility. Not perfect, but little risk, certainly in terms of the 100-year time horizon we look at. And fourth, there are many co-benefits with agriculture and many co-benefits that have been known for many years. If you think of nice wine growing regions of the world, most of them are based on basalt ridges or basalt soil. Okay, negative aspects of the ERW. It's in soil, it's in a natural setting, it's not in an engineered setting per se, so it's slow, it takes time. Although these technologies are well established, they're energy intensive, mining rock, grinding rock, all of these sorts of things that they're going on now. So they take a lot of energy, and depending on where that energy is produced, can have an associated greenhouse emission with it that's not moving in the direction we would like it to be. Third, some of these rocks contain toxic heavy metals. We can get into what that means in a little more detail shortly, but that is the reality depending on what's chosen. If we look at the difference between basalt and olivine. Fourth, grinding rocks into fine powders can be breathed in or ingested, so that can be bad for human health, but again, it's more pointing that out as opposed to something that should be a showstopper. And fifth, both monitoring and modeling is challenging. You have a dynamic system, and in many instances, it can be difficult just to get a weathering signal. So that should be acknowledged. In summary, our ideal conditions, which, and I'll preface this by saying there are extreme outliers like glaciers moving and these sorts of things, but if we're assuming parts of the world where it's not that extreme, the ideal conditions for weathering would be low pH, high water availability, high temperature, high CO2 partial pressure, and increased reactive surface area of the rock. My pointed to this before the meeting, but I guess just as a walk through the document, we have our 4 general principles, which as they stand in the document at the moment, again, this can evolve, I'm happy for it to. I've outlined them up front, and they're the things that we're really looking to emphasize, which is transparency, which is absolutely critical with all methodologies, but particularly with this when it comes to simulation. Application of evidence, the MRV, and then acknowledging that this needs to be refined over time. We have to learn, we have to refine, we have to calibrate and validate through time. So that really, again, needs to be emphasized with this methodology. I don't really need to emphasize this. I'm sure everyone's relatively familiar with the ICVCM, but I suppose to point out these are new, relatively hot off the press, but standards and principles that we would like to align with at Puro moving forward, given that they're not perfect, but they're certainly a step in the right direction, we believe. Okay, separate chapter, which we haven't had before, around environmental and social safeguards. So why did I choose to do this? Well, we have potentially heavy metals in some of these rocks that are being crushed. They need to be analysed. This needs to be done and considered properly. And really, this boiled down to the following for me. But once we've spread the rock on the soil, it can't be undone. So if we haven't considered these risks up front and done it properly, once it's spread on the soil, then that's it. We can't go back and collect a bunch of rock powder without bringing all of the soil with it. So that's also something that needs to be really considered. So that was why we have a separate chapter on this particularly now. Thomas will speak more to this today, and we need to have more of a discussion about this as a group more generally. But for now, as a line in the sand, we are going with these threshold of acceptability limits from the EU regulation. They're outlined in the doc to you very briefly now, so that you're aware of what they are and where they've come from formally. I think that the important thing to consider with this approach is that a lot of these, well, the difference between inorganic soil improvers, in other words, fertilizing the soil, and what we're looking at here is fertilizer would ordinarily be done annually, would be spread on the soil annually, if not more. And this approach is something where we'd be looking at doing it going to be once or twice. So there's a lot that I guess guides us, but a lot that's also not necessarily applicable. So keep that in mind as well. We need to be sure that we're not allowing things to be spread that are going to cause environmental damage, but we're also not trying to set thresholds that are completely irrelevant and really don't help us to understand this in the way that it needs to be. Just a quick one, don't need to, it's contained in the document and outlined nicely in the document, but just to outline that we have, we're asking for an environmental risk assessment. Again, this gets back to the regulations for toxicity thresholds being very haphazard, inconsistent, and certainly not uniform. We have standards in place that are very strict that we can use to apply, but I think the best way to do it would be to consider it on a case-by-case basis and consider it in the following way based on the US EPA guidelines. So that's included there in the document. Then, as I mentioned, we have all rolled into one chapter nicely this time, our eligibility requirements and the verification of those requirements. So these are the individual subheadings that we have within the document, but for today, I just wanted to focus on the environmental safeguards, the quantification dimensions of that chapter. So the environmental safeguards are put in place so that we're able to demonstrate safe rock sourcing, which I think speaks for itself. We're wanting a geochemical assay for this methodology, which serves two purposes. One, to make sure that we're not over the toxicity or toxin thresholds, and also to drive a modeling result, because that inevitably will have an impact on that as well. So one report or one piece of analysis that serves two purposes, a risk assessment, as I've outlined, which I think is appropriate. And for now, we have the EU thresholds that I've outlined, and Thomas can speak to that a little bit more after I've finished. So then the second part here is quantification. I'll come to this at the end as well, but making sure that we have site-specific parameters, again, geochemical analysis, and that we have a simulated result provided and validation. So these are things that we really need to consider with the likes of Mel and Undo and Noah in terms of how they're simulating a result and how they're looking to validate that through time. I mean, to emphasize again, it's a slow process. So if we're looking at deriving a result in the short term, we need to be very transparent with how we're doing that and very transparent with how that's being validated. Point of creation of the cork. So in other words, what people would be paid for. As it stands at the moment, we have two approaches. This isn't simple, as you can imagine, but we've come up with two approaches. So one is to provide the certificate or the payment 1 year after the spreading, based on the fact that the simulated result has been validated. Second approach, which I think is probably more robust, but again, this needs to be discussed and can be brought up in the Q&A, where we have an activity-based payment and a result-based payment. What does this mean? So activity-based payment, in other words, you can actually prove that you've spread the rock and something has actually occurred. So, and this is expensive. So if we're thinking about project developers, project proponents getting this sort of work off the ground, if they're having to actually physically go out and do that work, it costs money, it takes time, it takes people to do it. And if nothing is compensated and they have to wait years into the future to be compensated for that, it may mean that we don't really get much started at all. And the second dimension to that can then be a result-based payment, which can be made after 3 years as an estimate at this stage of validation of that simulation result. So in other words, collecting data through time and validating what was theoretically meant to happen based on the underlying assumptions that have been made transparent. I'll throw quickly to Ilias now. If you would just like to talk through this one slide, that'd be great.
So there are many challenges with enhanced rock weathering modeling, but one of the things that is rather easy here compared to other removal method is actually to define the boundaries, the goal and scope of the life cycle assessment. So in chapter 6, we define this goal and scope and how the LCA has to be performed. And if we go in these details, briefly, the functional unit we defined for the LCA, it has to be 1 ton of rock applied at a given location, application rate, and granulometry. That's the unit we're going to use for measuring all the rest and report the results. Then in the method, we also define clearly the system boundaries. So what processes have to be included in it. And that's what it's both explained in text and also through this generic flowchart that you have here on the right. And so in the LCA, we have to include the supply chain for the rock, its processing, so all these energy intensive steps, the transportation to the application site, and the spreading. But that's so what happens up front. And then you have also to include maybe some monitoring activities and other processes that you may need to implement for the weathering phase and the monitoring in the environment. Then we also stress explicitly in that method, like in the others, that it has to be a full scope of emissions included here in the LCA, and that means all greenhouse gases, not only fossil CO2, but also methane, N2O, and others. And you have also to include both the foreground and the background activities. And by background, we mean, the infrastructure, the manufacturing, and the disposal of everything you're using there. So it's not just direct energy use, but a bit more than that, full LCA. We also give guidelines on what type of data, of LCA data to use, and that's called the system model in LCA. And so we recommend using what we call a cutoff system model as defined in various LCA databases. And when it comes to multifunctionality, so the case where you would have co-benefits or other materials being substituted, we recommend to not perform any substitutions here and to account and attribute all the emissions to the removal activity, which is a way for us to be here a bit more conservative. And finally, we stress that the results provided must not be a single number, but they must be presented in a disaggregated form, showing contribution analysis from different life cycle stages and from different greenhouse gases. And that's for the transparency of our LCA reporting that we require this. Yep, you can continue, Leonard.
Thanks, Elias. Okay, so I'll let Noah unpack this in more detail, but just to give you guys, again, a walk through the chapter, we've tried to simplify the equation as much as possible, but don't be fooled by that simplicity. There's a lot tied up in e-stored and there's a lot tied up in e-supply chain, but I think this is a nice way to simplify it. The key thing that I want to emphasize is, and for all of you to be aware, we have a simulation result and we have a measured result. So we need to keep that in mind at all times. We're looking at approximating something that's happening slowly through time, which is why we need a simulation. And then we have to go and measure that to actually validate whether or not that is a version of reality. I won't emphasize this again. This is just one of our e-supply chain is considered in the LCA, which Elias has just gone through. So I don't need to go through that again, but the e-stored, which I think should be fairly straightforward to everybody, but the amount of carbon dioxide captured by the weathering rock that's been applied to the soil. So we have a weathering time, we have a time horizon, but for a certain quantity of rock, we're trying to work out how much carbon, in layman's terms, has been sequestered by that rock over time. And again, emphasis on simulation and measured result. So the requirements for the simulation-based quantification approaches, I think before Noah goes through these today, this is general to all, and I'd just like to state this up front as a mental primer so that when Noah goes through his approach or their approach at Lithos, that this is in everybody's mind. So for all projects, we have the project specificity dimension, which is the project parameters at the site, acknowledging that it's a dynamic simulation through time, which it will be for all approaches. It's a system dynamic model, effectively in a dynamic environment, so that, i.e. the parameters aren't controlled, can't be controlled easily. We have an uncertainty estimation stated up front, And all of this is like transparency is the key to all of this. This is what we're asking for, so that it's very clear, so that if someone comes along and says, okay, theoretically, what have you sequestered after year 1, year 5, and year 10, and what have you gone and measured, that it's very clear what's been done and why, not hidden in a black box. We have empirical inputs and monitoring that's provided up front. Simulation validation, I mean, how this will be done, we will find out in time. We need to actually start, but the simulation has ideally been validated in some form. If not, we've been provided with a substantial amount of information for how that would be done, that it's made publicly available. I guess maybe David can speak to this at the end as well, in terms of how this will evolve, so that we don't come up with everybody having individual models and approaches that in the end isn't building the overall body of knowledge for all of us and for the industry in general, which is very important. So we're all learning together. I think that's also something that I would like to emphasize, certainly on the journey we've been on with the working group, just to produce this document. If we're not all working together, then and everybody's working in their own individual silos, it's such a difficult thing to understand and to build knowledge and experience with it. Yeah, it would be. It's not a one-man undertaking. It's a real team effort. And simulations and assumptions. So everything that underpins that modeling has been transparently communicated, so that we're aware of what's going on and we're not getting into a black box paradigm. But I will let the other two gentlemen speak to that. So that's the end of my section. Thank you all very much. And thanks to the working group enormously for helping me put that draft together. I couldn't have done it without you. So with that, I'll throw to Thomas, and then Thomas can throw to Noah, and Noah can throw to David, and then we'll bring things to a conclusion in terms of the presentations before Q&A. So over to you, Thomas, and thanks all.
Okay, so let's see what I have here. You gotta tell me whether you probably don't see presentation now, do you? Everything's becoming a bit slow here.
We can see your PowerPoint, but it's not in full screen. Yeah. And
is it full screen now?
I think it's in presenter mode.
Okay.
Yeah.
I never know. Did that help?
Yes. Yeah. We can see it.
Okay. So I was asked to give a perspective on safeguards on the chapter for safeguards for toxic contaminants, and why it's so hard to come up with a general framework that would fit for every enhanced weathering project. Where's my mouse? Here it is. Yes, and one sentence I took from the draft was that not all soils are equal, and for starters, that's already very important when you think about where you want to have your enhanced weathering project, because whether it's extensive or intensive agriculture, that can really make a difference. Because of course, in this first intensive agricultural scenario, you might be mostly concerned about crop yield, nutritional value of your crop and things like this. Whereas in this other example of, for example, like alpine meadows that are extensively used for agriculture, biodiversity really becomes an issue. And here I have a picture of this Arnica montana, which at least in Central Europe is used for a lot of medical purposes. And this flower really likes acidic, nutrient poor soil. So if you start to increase pH and if you start to fertilize a lot, this might be good for climate change perspective, but from a biodiversity perspective, this might also do a lot of harm. So, but that's just for the starters. But now, even if you stay with intensive agriculture, and here I'm going to talk more about a German framework, there's a lot of different pathways you have to consider for your contaminants, because you've got to consider contaminants moving into the crops, moving into the soil, or moving into the groundwater. And each of these pathways will have different regulations, that different national regulations. And as you said before, for the inorganic soil improver, it's easy because we have this European Union regulation, at least, that gives us some acceptable threshold limits for contaminants that we can consider. But then we have to think about that, for example, not every potential contaminant is considered in this regulation as, for example, uranium, which is also sometimes, you know, part of rocks. And then this regulation is also made for agricultural purposes, for which normally for fertilization purposes, you would not use as much rock powder as you might want to use for enhanced weathering purposes. So when you talk about enhanced weathering, you can't just talk about milligrams per kilogram, but you also have to consider the fluxes. You have to talk about the kilograms per hectare per year and think about what that does to your soil, what that does to the groundwater, in addition to this regulation. Yes, so moving into German regulations, once you applied the powder, you might want to think about what's happening to the soil and how is this important for soil quality. There things get a bit more complicated because European Union doesn't have any competence for law giving for soil protection or soil conservation. That's all based on nations, if at all, in Europe. So for example, in Germany, you have the Bundesbodenschutzgesetz or the Ersatzbaustoffverordnung, which is dealing with those issues, and there you find guidelines for how to classify your soil if you were to use it, for example, on another field. Like, I don't know, land use is changing, you want to take your topsoil, move it to another field which has lost some to erosion, and then you would move into those tables. And those tables, for example, in Germany, they really make a difference whether you talk about a clay soil or silty soil or sandy soil, and the maximum acceptable, for example, nickel value that you can have in there in order to still be allowed to use the powder wherever you want to. So this is why we need specific approaches instead of a general framework. Gets, of course, even more complicated because this is one thing, but then you also have like a natural background of all contaminants which are normally related to the geology. And here, for example, you see a map of arsenic in topsoil in Germany. And because of that, for example, in Germany, you have lower local authorities, and they all come up with their own threshold values that they will accept. So you can't even stick to the national law. You gotta go to the local authority and say, like, hey, what's the threshold value here? And for example, in central Germany, they would consider like a 1 to 2 mixture of soil and water. That's how they test it. They would consider 40 micrograms per liter still perfect. And 100 kilometers north in Niedersachsen, they would say like, no, 15 is already anything we can use. And I'm not even saying that these are very smart values, and I'm sure some people just roll dice sometimes when they put them in there, but that's what you have to deal with, at least in Germany, and it's the same in Austria, basically. So a lot of things to consider, at least land use change, impact on biodiversity, and then you have to think about the different pathways that contaminants can reach humans, which is soil human, groundwater human, crop human, and they all have different regulations that you have to adhere to. Quick last slide. This doesn't mean, from my perspective, this doesn't mean that we have to be overly cautious when it comes to enhanced weathering projects, because trade-offs are a common thing for fertilizer users, right? Because we know we have uranium problems because of our phosphate fertilizers, but that doesn't mean we stop using them, because we also need the phosphate, and we know that. So we have to do it. The same is, we know we get problems with drinking water, nitrate in drinking water, but we don't stop manuring our fields because of that, because that's how our agriculture works. We have to manure the fields. So I think quantifying the acceptable risk and quantifying how much milligrams per kilogram we might be willing to increase nickel or chromium in our soil really requires us to focus on the associated benefits of enhanced weathering. And if we make sure that the project developers focus on those benefits and not only on the regulations, I think this is an additional safeguard that can really ensure that enhanced weathering projects are not causing any harm. And of course, that's why I'm here. We need field trials for that a lot in different scenarios, different soils, different climates to find out more about what the benefits are and where they apply best. So that's already from my point. So I'm going to stop sharing if I can find the mouse. Yes.
Thanks very much, Thomas. Much appreciated. Noah, calmly, and when you're ready as well. Okay, perfect. We'll throw to you. over to you, mate. Thanks very much.
Fantastic. But yeah, I'm excited to be able to walk through our approach here. Think of this as an example of one of the simulations. So I'm going to do two parts here. I'm going to really talk about how we actually make measurements to compare to our modeling framework, and then walk you through what our modeling framework is. Yeah, so the basic idea is we have a little bit of a different take on what should be in a MRV framework or a modeling framework than some other folks doing this. But the basic idea from our approach in practice is that you need to track what's happening in the soil, what happens to the products of weathering at a soilscape as they move through surface waters, and then track what happens to those products in the ocean over a set time frame that is determined to be permanent, whether that's 100 years, whether that is 1,000 years. So we're going to start on really our approach of actually tracking this with geochemical measurements in the field, and then walk you through our modeling framework here. Okay, so we're taking an approach where, in order to get an integrated look at what's happening with carbon dioxide removal, we're focusing on solid phase products. So focusing on the basic chemical composition of soils instead of focusing on waters. The idea from this is very simple if you think of it in a distilled fraction. If you imagine mobile components and immobile components of basalt, you can imagine a mixing relationship with soil and the mineral feedstock that you are adding to drive carbon dioxide removal. As carbon dioxide removal occurs, as weathering occurs that's capturing acid from that system, you will deviate from this mixing relationship, which is represented by this trajectory here, in your actual sample that's a mix between these two end members, right? So this is showing it as magnesium. As you remove magnesium from that system, in your solid phase product, that is acid being removed, CO2 being removed from the system. So the basic advantage of this is that it's time integrated instead of providing a snapshot like a water does. This also directly ties into what people are already doing for standard agronomic processes, right? In most places where you're actually doing row crops, you will have yearly soil sampling to determine the amount of fertilizer that you need to have on that system to give you maximum yields. Some of the problems with this are thinking about the actual field, the signal to noise ratio that you have, and field scale variability. So even though the approach that I laid out to you on the previous slide is very straightforward, one of the problems is that in practice, we're actually at the very low end of this mixing relationship. And what this means is you actually need to have measurements that have low amounts of error, that are both accurate and precise. So if you use measurements that are from a standard commercial lab, you will fall into with a lot of application rates where the analytical uncertainty is too great to actually resolve this signal of weathering in your system. Okay? So we have dealt with that problem by just coming up with a method that is much more precise and much more accurate than you would get in standard commercial labs. We do that by utilizing a relatively old technique where you add a spike from the rare isotope into your sample before injecting it into our mass spectrometer, which in this case, for greatest accuracy and precision, we're using this is an absurd name, but I'm going to do it anyway. A inductively coupled plasma mass spectrometer. So what we're doing is isotope dilution magnetic sector inductively coupled plasma mass spectrometry, which sounds like it's something that would be relatively not relatively widespread, but actually this is something that could be applied to a wide range of commercial labs and is something where it's actually used, a common tool in environmental geochemistry. And more importantly, from thinking about how widely this could be applied, is something that is also commonly used in the biomedical industry. Okay, so applying this approach, what we find and why we think that it's critical to actually have something that is a detailed methodological approach, or actually have empirical constraints on this, is that in different systems, the extent of weathering that you have over a time frame can vary dramatically. In some systems, it can be very negligible amounts of weathering, represented foremost in alfalfa systems in the Midwest, into systems like sugarcane and low pH corn systems where you can have very high extents of cation loss from your solid phase, which you can directly translate into an extent of carbon dioxide removal. Okay? So this is our empirical way of demonstrating the amount of carbon dioxide removal that is occurring in the soil, the instantaneous carbon dioxide removal that gives you a time integrated look at the process. Okay. The other approach of doing this, or what we compare to on the model side now, is we have a reactive transport model. It's of course part of everyone that develops geochemical models to have an acronym for their geochemical model. The name of ours is called SEPTOR, which has only a mildly force set of names attached to that. So this is in many ways has some of the same core components of any one-dimensional reactive transport model. However, I think that we have a couple aspects of that that are will allow it to actually perform much better in a wider range of circumstances. One of the main aspects of this is that we have a spin-up from the system that can tie into a previous land use. And we also importantly have an exchangeable fraction in that. This is important since many of the signals for carbon dioxide removal actually don't move out into surface waters for a multiple year time frame. This is posted on GitHub. It's written for folks that are very interested in the model side. It's written in Fortran, which allows it to be very computationally expensive and is roughly 20,000 lines of code. One of the things that also we're very excited about for our framework is it's actually designed to be a combination of a mechanistic model grounded in basic chemistry and physics. And then on top of that actually has a machine learning component, something that's already implementable. This obviously, as we will mean that the actual framework we're using is going to be continuously evolving, and we're going to, as we generate more data, develop a better ability to actually predict what is happening. So this is some looking at natural silicate weathering frameworks, but it's the same it's the exact same framework we're using to predict enhanced mineral weathering rates. So if you look at this where we have all of the parameters that we'd like to utilize this, this is where we're forcing the machine learning framework with 32 separate parameters. So this would be representative of, say, the American Midwest. We can predict roughly 96% of the variability in the data. This is comparing at a catchment scale, the predicted, this is the simulated weathering results, and then the actual real measured empirical results from this. If we move to a system where we have a little bit less information for land use change and for other conditions, so think of this as representative of portions of Brazil, for instance, the uncertainty moves to something closer to 80% instead of something that is at a much higher level. The next part of this framework is actually having the weathering products move through a river framework. So we have river networks actually be naturally emerging from digital elevation models. This is the example from the US, which you can't actually see because it's relatively dense, just looks like a orange blob. An easier way to do that is remove the smallest streams from that component and focus on a single network. So this is the Mississippi River network. So what our framework does is as you put alkalinity and cations into the system from weathering, for instance, in my farm in Wisconsin here on that blue dot, or I should say my family's farm, on this blue dot, it would move into the Mississippi River and eventually flow out into the Gulf of Mexico, but it'll actually interact with all of the rivers that are in this defined network. So in each river segment, we'll have a dynamic chemistry that's evolving as the system moves out into the Gulf of Mexico. And what that allows you to have, because all of these rivers are interacting, is to have the carbonic acid system actually continuously re-equilibrating along the transport of your weathering products as they make it out into Gulf of Mexico. Right, so this is showing the PCO2, for instance, in all of the river networks in the US. It also allows you to have precipitation of solid phases. This is showing, for instance, the saturation state, which the geochemical parameter that determines if we will have precipitation of solid phase minerals, which will release CO2 from that system. Okay, and almost done. Last part of this is we don't only need to see what happens when we put it into the ocean. We also need to be able to, over a decade, 100-year, or even 1,000-year for some buyers potentially, be able to say what happens to those weathering products, how much of the carbon is stored in the ocean. We've been doing this with a Earth system model, which refers to a Sea Genie, which performs very well relative to both modern observations in the marine realm, or in future simulations compares very well to CMIP or IPCC class models. So what it allows us to do is we put a pulse of alkalinity into the river at any single point. So in the case of my farm, it flows down the Mississippi and eventually it ends up in the Gulf of Mexico. And then the model which has a fully dynamic, has dynamic oceans, allows CO2 to exchange with the ocean interior and the atmosphere, will give you an amount of carbon that actually remains stored in the ocean relative to what would be an emissions reduction or a direct air capture scenario. So it's showing in gray here the weathering inefficiency relative to what is a background direct air capture or emissions reduction scenario with a roughly 10% CO2 efficiency at a different emissions trajectory, which would be the RCP 2.6 or 8.5. So that was a lot in a very short time period, but what I wanted to get out of that is a sense of what is our framework, what are the things that we're accounting for, and what things have we outlined in the document that Leonard walked through. Just to give a shout out to, I presented that like it was something where I did, of course, which was not the case. So it was a very brief acknowledgement to the team that's working on our framework here.
Thanks enormously, Noah. That was fascinating. Really appreciate it. And apologies, Chris, I popped it in the chat for everyone, but I didn't see you on my wall of people earlier. But yeah, just to outline, Chris and Noah work together. So thanks for also joining us today. Greatly appreciated. Yeah, thanks enormously. David, I'll throw over to you to bring things home for us, and then we can move to Q&A. Thank you.
Okay. So you see that?
Yes, full screen. Good to go.
Okay, great. So this is really just a few slides to introduce a new enhanced rock weathering carbon dioxide removal into comparison project. And that's even more of a mouthful than inductively coupled mass spectrometry. So we've got a funky acronym called RockChip. And this is really a project that grew out of discussions with Noah and Chris over the summer. We both realized we had sort of models that were dealing with enhanced weathering and in related, but not the same way. And we started thinking, well, it'd be interesting to do a comparison between our two models. And then we realized actually, you know, there's more of a project here if we start thinking about enhanced weathering and carbon capture more broadly. And so the project really just has, you know, it's still germinating, and the project has sort of three broad goals. And the first one is really to try and build an alliance of enhanced weathering groups, which goes back to what Leonard was saying earlier. You know, we can't have different groups going off in different directions, you know, or we want to try and avoid that if we can. We also, you know, relatedly want to take the field forward through consensus. We feel it's very important to increase the credibility of enhanced rock weathering carbon removal models, you know, particularly for the policy arena, for carbon credit certification, which is what we're discussing today, but also for the science. And we need to understand and quantify model uncertainties. So, you know, the motivation which relates to the goals is really fundamentally, we need to know, do these models that the different groups are producing, are they giving us realistic CDR numbers for agricultural systems over time, over different time horizons? You know, do we believe them? Are they credible? And you know, the interesting point here is a lot of the enhanced weathering models that are out there, they all have the same, some of them have the same core components, like the mineral rate weathering equations. But it's how those equations are embedded within the soil profile, how many soil layers they have, how do you deal with things like hydrology, particle size distributions, and biology. These are some of the issues of the models that differ. And so then the question is, we need to understand and quantify how these differences translate into enhanced weathering rates and also uncertainties in CDRs. So this isn't really the presentation to go into detail, but some of the aspects that we're keen to look at here are to develop and execute protocols for model validation. How do we go about model data comparisons? And can we develop protocols that are rigorous? And then benchmarking model performance. We need to try and look at fast and slow weathering basalts, warm and cool climates, different types of soils. And so it's critical that we do validation, but also look at sensitivity of models to these different parameters. And just to kind of give you a sense of some of the things that you could do, you could look at different mineralogy, but keep the weathering mineral kinetics the same. You could look at different particle size distributions and sizes, different climates. Hydrology, so the precip minus evaporation, which basically equates to the vertical flux of water through the soil profile, which relates to weathering. Soil profile, so all of these sorts of inputs you could standardize and then vary one thing and look at how sensitive the models are. And crucially, again, coming back to the point that Leonard and Noah are making, it's no point just doing these for 1 year. We need to look across different time horizons and see how the models compare. So we're still evolving our thinking here, but we've got some kind of initial broad thoughts on the board. So for the past few months, I've been reaching out to various folks within the community, and the modeling teams that have kind of signed up so far. We've got 7 different groups. My group, Noah and Chris, Ed at Yale, Jim, Mel at Undo, some folks from Lawrence Berkeley, Daniel Gold and Philip Caius, and also the Italian groups. And then we've also had sort of positive response from folks that say, look, we haven't got models, but we'd be willing to share the data. And so we've got a bunch of data teams as well. And the idea is really to test, evaluate the models, not only against field trial stuff, but where there's sufficient information to parameterize the models, compare it with Musicosm. And we've got a nice selection of folks that are offering us data sets. And again, there's going to need to be some kind of quality control on the data sets, as well as a minimum number of things that they can collect that the models will need to parameterize themselves. And we reckon there's probably, very broadly four end products, probably some kind of high-level synthesis paper where we try and report community consensus on enhanced weathering, what the uncertainties are, whether we can do ensemble simulations with multiple models to characterize uncertainty. I think Leonard and Noah touched on this as well. We absolutely need to have the source codes open for transparency and available on GitHub or wherever. We need to understand, if we get differences between models, we need to understand why we've got those differences. And it may be that we can flag up recommendations for what to measure and how frequently to make those measurements from field trials as this kind of model data validation exercise proceeds. I'm sure, undoubtedly, as we kind of proceed with this project, more will appear. As I say, we're just at the kind of germination phase of this. We're going to have a website, hopefully this side of Christmas, and then we'll sort of kick on more in the spring of next year. And that's all I've got.
Thanks so much, David. Greatly appreciated. I think that emphasizes and brings together nicely a lot of the points made by all of us. Really appreciate it, and that work's going to be incredibly important going forward for all of us. I think if we just pause for now and terminate the recording, that'd be great.